Hi kidlets. So we left off looking at the different orbital positions of the Earth and the Moon as it orbits around Earth. And I apologize, some of my font got functified here. But as a consequence of us having an elliptical orbit, we have these different orbital positions. So in terms of Earth, we have our perihelion position, which is closest to the Sun. We have our aphelion position, which is furthest from the Sun. And then in terms of the Moon, we have apogee and perigee. So helion is in terms of rotation around the sun, and perigee and apogee is any body orbiting a primary body. So the moon orbiting us would be apogee and perigee. And these different positions have a huge effect on how we see solar eclipses. So some definitions. So partial eclipse, you guys saw this with the sun this year and also with the lunar eclipse. So this is when only part of the sun is blocked out. And the rest of these definitions are only for solar eclipses, not for lunar eclipses, because remember that the Earth is so much bigger than the moon, 6 times bigger, so it's a lot more favorable to create conditions where the moon passes into our umbral shadow than where the moon completely blocks the sun, because the sun is so much larger. So a total eclipse is when completely all of the sun is blocked out, and remember that a solar eclipse like this would have been viewed during broad daylight, and it would have made it completely dark if you were in the path of totality. An annular eclipse does not mean it happens annually, but this is when the moon is at apogee. So remember, the apogee is the position in its orbit when it's further away from the Earth. So when the moon is further away, it has a smaller angular diameter and does not completely block the sun out. So the importance of eclipses is that it allows us to understand some important processes like helium production and nucleosynthesis in all stars. This is where you have hydrogen that combines together, overcomes the tremendous force of repulsion between 2 hydrogen atoms and forms helium. The temperature of the corona, which is this outer layer of the sun, it is the hottest layer of the sun, and it extends about 40,000 kilometers away from the photosphere of the sun. The role of magnetic fields and their production of energy around the surface of the sun, which is what solar flares are. And those are all things that solar eclipses allow us to see. So just some differences in sizes between the moon at apogee and perigee. So perigee is about 219,000 miles away, apogee is 251,000 miles away, and you can see just the difference in angular size between perigee and apogee. So the different phases of a total solar eclipse. So you can see here the beginning as it's starting to, as the moon is beginning to cross in front of the sun and progressing all the way to a total eclipse. So here you can see as the sun is completely blocked out, we can see these prominences in solar flares. The chromosphere and the corona are only visible during a solar eclipse because these do not emit visible light. These are only visible in UV and infrared, which the naked eye cannot see unless we've completely blocked out the sun. It looks like my animation is not playing. I'll play this for you guys tomorrow. So we don't have eclipses every month because the orbit of the moon and the orbit of Earth are not entirely lined up. And hopefully this is one question that you've asked yourself so far, is why we don't have eclipses every time we have a new or a full moon. So remember that the ecliptic is this path of the equator of the sun that most things in the solar system line up with. So Earth is only slightly off. Most all of the planets are only within 4 degrees of the equator of the sun, except for Pluto, which is like 17. But the moon is off of that orbit by about 5 degrees. So when it crosses that, we call that a node. So here, when it's on the ecliptic and on a node, is favorable for eclipses. So it has to be the correct moon phase, and it has to be on a node in order to have an eclipse. So here we can see again, we've got a solar eclipse. This would be new moons, this would be during the day. So here we've got a lunar eclipse, this would be a full moon, which would be at night. And here we can see the slightly offset orbit of the moon from the ecliptic. And this is off by about 5 degrees. This is not 50. This distorts my text. It should be 5 degrees, not 50. Sorry about that. So again, here would be our solar eclipse, there would be our lunar eclipse, and we can see how slightly off the orbit is. And it has to be on a node on the ecliptic. Otherwise, just as you can see here, you don't have an eclipse. Here, you don't have an eclipse. So this slide has gotten slightly distorted as well. So E is for eccentricity. It's only slightly elliptical, and we'll talk about this more in the next unit. This is the average distance of the moon, is about 384,000 kilometers. So at perigee, 363, at apogee, 405. And its orbit is off by about 5 degrees, which is why we do not have them every month, and we can see that difference right here. So here we can see what the different angular diameters of both the moon and the sun would appear, both at perigee, apogee, perihelion, and aphelion. So here again, just looking at the moon, we can see the difference in angular size. So when the moon is at perigee, meaning it's at its closest, we can see the size compared to when it is at apogee, which is when it is its furthest. So then here we can see the angular size of the sun as well. So when we are the closest to the sun, when we are at perihelion, there would be the angular size of it, and when we are furthest from the sun, at aphelion, we can see how the angular size changes. So much more dramatic, perigee and apogee of the moon, because Earth's orbit is nearly circular. It's nearly a perfect circle. It's very slightly elliptical. And here we can see this picture. This is an annular eclipse of 1994. So here the moon would have been at apogee, and it does not entirely block out the disk of the sun. So it would have an outline of orange. So you can see you cannot see the corona, cannot see the chromosphere. So here is an almost total annular eclipse. These can also be known as the diamond ring effect. So here again, looking at the annular eclipses where we can still see the outer disk of the sun. So this is when the moon is more distant, when it is at apogee, and has a smaller angular size than the sun. So here is that diamond ring effect again. When it's at the diamond ring effect, it's further in its orbit, but we can still almost completely block out the sun, but not entirely. We can see that bit of the sun showing through. So here we can see the solar chromosphere during an eclipse. This is the only time that this can be viewed without special equipment. We can see solar flares, we can see prominences. So the chromosphere is this area outside of the photosphere, photosphere being the lowest layer of the sun, and then the corona would be this outer layer. So here we can see our eclipse calendar. Sorry, that was my toddler. Here you can see this eclipse calendar, and our next visible from the US solar eclipse would be this guy right here in 2017. I think it's in February. I know it's this guy. So August. And that one is on my bucket list. So the one that is on August 21st. So special viewing tools. This would only be for a total solar eclipse. This wouldn't have worked for ours necessarily due to the partial nature of it, but we might have been able to see it that way. So eclipses occur in this cyclic pattern. So, and again, it's pretty amazing that the Mayans had calculated this every 18 years, 11 days, and 8 hours exactly when an eclipse will hit the exact same place again. So these follow a cycle and a pattern. So that's called the Saros cycle, because Saros means king. And early on, it was kings and their advisors that were able to calculate this and then really exhibit this dominion and fear amongst the people because they could predict when the sky was going to go black. So here is looking at that Saros cycle again, and this is all based on the pattern. So here would be where there would be an eclipse, and here would be where there would be an eclipse. And here are the different paths of eclipses. So they would follow the same place, the same shadow would hit it every 18 years. So that is it, guys. I will see you tomorrow, and remember that your test is going to be on Thursday.